In 2026, developers of AI content detectors claim up to 94% accuracy, yet data shows these tools penalize the highest quality human writing. Detectors do not measure actual text origin, they measure statistical proxies, specifically perplexity, which is the predictability of word choices, and burstiness, which measures structural variation in sentence length. Formal academic writing and non-native English naturally utilize highly consistent grammar and restricted vocabulary. This lowers their perplexity, pushing organic human text into an overlapping statistical range with AI outputs. The 2026 data quantifies this failure. While overall false positive rates hover between 4 and 16%, writers using English as a second language, or ESL, face up to a 3.5 times penalty compared to native speakers. Automated paraphrasing tools, often called AI humanizers, exploit these exact mathematical boundaries. By deliberately fracturing sentence lengths to artificially inflate burstiness, they bypass post hoc detectors at a verified rate of 99.3%. Evaluating predictability after a text is generated cannot definitively prove its origin. Post hoc detection is a statistical guess, not a mathematical guarantee. The alternative to this guessing game is generative watermarking. Rather than trying to identify AI patterns after the fact, generative watermarking requires the language model provider to secretly alter the model's output distribution during the creation of the text itself. To be viable, a generative watermark must mathematically prove the text's origin without degrading the semantic quality of the model's output. The foundational baseline for this cryptographic injection is the KGW family of watermarks. KGW is an algorithmic framework that subtly modifies token selection based on prior words. Injecting a cryptographic signature directly into a language model's generation logits provides absolute provenance, but doing so forces a severe mathematical trade-off. In a standard autoregressive generation step, a token passes into a language model to output a vector of logit scores. Logits are the raw, unnormalized predictions a neural network calculates for the next possible word. The KGW system analyzes an H-gram window, a sequence of the preceding H tokens, and uses them to calculate a cryptographic hash. This hash acts as seed, randomly partitioning the entire vocabulary into a green list and a red list. A positive mathematical bias, represented as delta, is added to the logit scores of the green list tokens before the final probability calculation. The language model continues to generate text, but it operates with a statistically detectable bias towards sampling tokens from the green list. This embedded bias functions as a verifiable cryptographic signature. Its security relies entirely on the size of the H-gram window used to generate the hash. The KGW architecture is trapped by a mathematical limitation dictated by that window size. Consider a scrubbing attack against a large window, such as a 16-token sequence. A scrubbing attack uses basic paraphrasing to alter the generated text in an attempt to erase the watermark. If the window is wide, an attacker only needs to change a single token within that sequence to completely randomize the downstream hash, destroying the watermark for the next generation step. The logical defense is to shrink the window size down to 1 or 2 tokens, minimizing the surface area so the watermark survives minor sentence edits. Shrinking the window enables a spoofing attack. Spoofing is a statistical reverse engineering method where an attacker fabricates watermarked text to frame the original model. A small window drastically lowers the system's sample complexity. Attackers can query the model's interface to systematically map out exactly which short prefixes trigger the green list. This chart shows how spoofing success scales rapidly alongside query volume for small window models. For the KGW min model using an H=3 window, spoofing success rapidly hits nearly 100%, allowing attackers to inject malicious text bearing the model's exact signature. This graph plots the full empirical data, mapping scrubbing against spoofing robustness. Shrinking the window pushes the system to the bottom right, securing it against paraphrasing but leaving it completely exposed to spoofing. Enlarging the window pushes the data to the top left. Spoofing is blocked, but a single edited word scrubs the watermark away. This inverse relationship was accepted as a rigid mathematical boundary, necessitating a total architectural redesign. The new engineering directive is clear: maintain the spoofing resistance of a massive window while achieving extreme redundancy against scrubbing attacks. The solution relies on Proposition 4.1, a mathematical theorem recently published at NeurIPS. NeurIPS is an annual conference focused on advances in machine learning and neural networks. The approach is highly counterintuitive. Deliberately shrink the output space of the hash function. By heavily restricting the available outputs, the system statistically forces hash collisions to occur constantly within the large watermark window. This creates equivalent texture keys. Instead of one token generating one hash, multiple preceding tokens independently derive the exact same cryptographic cipher. This solves the scrubbing problem. If an attacker paraphrases a single token in the window, the remaining equivalent tokens still independently calculate the cipher and trigger the detection. The raw implementation of this theory has a critical flaw. Severely reducing the hash space destroys the diversity of the green and red list partitions. Equivalent keys provide necessary redundancy, but applying them to the entire vocabulary degrades the language model's predictability and output quality to an unusable state. To preserve the equivalent keys without sacrificing quality, the researchers engineered the SEEK algorithm, which stands for Sub-Vocabulary Decomposed Equivalent Texture Key. This diagram illustrates the architectural divergence between the flawed global approach on the left and the SEEK decomposition on the right. In the standard variant, the constrained hash space derives a single vocabulary partition. Unused permutations are dropped entirely, resulting in low diversity. SEEK resolves this by splitting the entire language model vocabulary into multiple disjoint subvocabularies. Each limited hash value now only controls the green and red partition for its specific subvocabulary, rather than dictating the entire dictionary. Once the subsets are partitioned, they are merged back together to form the final, unified green list. SEEK maintains the high density of equivalent keys for scrubbing resistance, while the combination of independent subvocabularies guarantees an exponentially larger set of distinct green list combinations. This chart measures relative log diversity, proving that this mathematical decoupling maintains text quality perfectly. The SEEK variant operates at a log diversity nearly identical to unwatermarked organic human text. Returning to this graph, the final performance metrics show the SEEK data points entirely detaching from the baseline trade-off curve. Isolating themselves in the top right quadrant, SEEK implementations achieve up to a 92% gain in spoofing robustness over baselines, without sacrificing true positive detection against scrubbing. By forcing deliberate hash collisions and systematically decomposing the vocabulary, SEEK engineers its way out of the Pareto frontier, delivering a mathematically uncompromising watermark for generative AI.